Welcome to this course on machine tool technology. Machine tools are the backbone of manufacturing industries. They are the devices that shape raw materials into usable parts and products. From simple lathes to advanced machining centers, machine tools must be designed not only for precision but also for strength, stiffness, and durability. In this course, we will examine the mechanical and structural aspects of machine tool design and operation. The learning is divided into two modules. Module 1 will cover the kinematics of machine tools, alignment and rigidity, and structural design for stiffness. Module 2 will focus on spindle assemblies, bearings, design for strength and stiffness, and vibration control of machine tools and their foundations. By the end of this course, you will understand how machine tools are designed, how their structural and dynamic properties influence performance, and how engineers ensure reliability and precision in machining operations. Module 1: Kinematics, Alignment, and Structural Stiffness. 1.1 Kinematics of machine tools. Kinematics refers to the motion of parts without regard to forces. In machine tools, it describes how cutting tools and workpieces move relative to each other to generate desired surfaces. The kinematic system of a machine tool includes the workpiece motions, such as rotation in a lathe or translation in a milling machine. The tool motions, such as cutting, feeding, and depth adjustments. The auxiliary motions, including rapid approach, return, and tool change. Proper kinematic design ensures smooth transmission of motion, minimizes errors, and improves machining efficiency. For instance, the geometry of gear trains, lathe screws, and feed drives directly determines machining accuracy. 1.2 Alignment and rigidity of structures. Machine tools must maintain precise alignment between the tool and workpiece. Even slight misalignment can result in dimensional inaccuracies, poor surface finish, or excessive tool wear. Alignment involves the accurate positioning of machine tool components such as the bed, spindle, guideways, and slides. Precision scraping, grinding, and assembly methods are employed to ensure alignment. Rigidity refers to the resistance of the machine structure to deflection under load. A rigid structure minimizes elastic deformation during cutting. For example, in a milling machine, the stiffness of the column and the bed directly influences the accuracy of the final workpiece. 1.3 Structural design for stiffness. Structural stiffness is critical for machine tool performance. A stiff structure maintains dimensional accuracy, supports high cutting forces, and reduces vibrations. Key design principles include using closed box sections instead of open frames to resist bending and twisting, minimizing overhangs in structural members, designing guideways and beds with wide, stable bases, selecting materials with high modulus of elasticity, such as cast iron, which also has excellent damping properties. The overall aim is to achieve high stiffness without excessive weight, balancing stability and cost. 1.4 Factors affecting stiffness and alignment. Several factors influence the stiffness and alignment of machine tools. Material properties: cast iron is preferred for damping, while steels provide higher strength. Joint quality: bolted and welded joints can introduce compliance if not designed properly. Thermal effects: temperature changes can cause expansion and misalignment. Load distribution: uneven forces on guideways or slides can distort structures. Designers must account for all these influences to maintain long-term accuracy. 1.5 Case examples in kinematic and structural design. In a lathe, the spindle and tailstock must remain precisely aligned to turn cylindrical parts accurately. In a grinding machine, even microscopic misalignment can result in poor surface finishes. In CNC machining centers, the design of ball screws, servo drives, and linear guideways reflects advanced kinematic design for high-speed, high-accuracy operation. In this module, we explored the kinematics of machine tools, emphasizing the motion systems that define machining. We studied how alignment and rigidity ensure precision, and we looked at structural design approaches that provide stiffness. The central message is that accuracy in machining depends as much on structural design as it does on cutting parameters.